So, hello everyone. Can you hear me?
Okay, so we can hear you.
Okay, thank you. So I would like to talk about Bnct dose calculation using FITS. And I think this is really specific lecture for person who want to do some BNCT simulation. So I think most of you know at least what is Bnct. So at the starting point, I will very briefly explain what is Bnct, but basically I think most of you know that. So Bnct is a radiation therapy for treating invasive tumor using a large neutron capture cross-section boron-10. And the tumor localizing drug containing the boron-10 is injected to patient and neutron beams are externally irradiated. Then alpha and lithium-6 are produced from the boron capturing reactions and deposit those locally. So Bnct is a selective dose delivery to tumor, protecting surrounding normal tissues realized. So this is a basic idea of Bnct. So the range of secondary charge particle is only 10 micron. So it's similar to the cellular scale. So FITS has been extensively used for this application, particularly for treatment planning system. So there are two treatment planning systems developed by in Japanese company, and one is Nucure, developed by Sumitomo Heavy Industries, and now it is used in several hospitals in Japan, and daily used for the treatment plan for Bnct in Japan. Most basic for accelerator-based Bnct. And the other application of the of FITS to Bnct is like a microdosimetric research. So if like a boron compound is taken into a cell or just attached to cell membrane, the effect should be different, and that's why the BPA is known to be more high relative biological effectiveness compared to BSH that can attach only at the cell membrane. So, and we try to reveal the reason from the microdosimetry. But in this lecture, I don't explain anything about this part. So maybe most FITS user who want to use FITS for Bnct is for this application. So I would like to concentrate on this application. So here is a basic setup of oh, sorry, I forgot to say that where is this lecture is in. So it is in FITS lecture therapy Bnct. And use the PPT file. So first, please run FITS with bnct.in file. So you see just a simple picture here. So this is quite simple input file. Epithermal energy neutron beam with radius of 10 centimeters are incident to the water cylinder with thickness of 10 centimeter and radius of 10 centimeter. And there are three tallies, one for visualizing the particle trajectory, one for T-track for checking the neutron and photon spectrum, and the one for deposit T-deposit for checking the dose in water cylinder. So let's change the ICNTL equals 0 and execute fits and check dose EPS and spectrum EPS. Okay, so let's run fits by changing this. So I think it's quite easy for you. So I also do it on my screen. Change 0 and save and run fits. Then check those EPS and spectrum EPS. So the initial neutron energy started at 10 to the minus 5 MeV. Then these neutrons are summarized in the water target. And some summarized neutrons cause captured it by hydrogen atom, and the hydrogen atom generate 2.2 MeV gamma rays. And the 2.2 MeV gamma rays are transported and sometimes decrease the energy like this. And here is the dose. So there are two doses for photon doses here, and the P5 group is no, actually, this is neutron dose. So looks like P5, but this is red line. So neutron dose is much lower. So those photon dose are dominant. So total dose is almost equal to the photon dose. So if you have any questions, so now we have only 9 participants and 2 are tutors, me and Abe-san. So you can directly ask questions if you have by turning on mic or send a chat message. Yeah, so don't hesitate to ask. It's a small class. Okay, so let's go to the next exercise. So change the mass fractions and add 10 ppm boron in water. So here, material is defined by H2O, but usually the boron density is given in the ppm, and the ppm is a weight mass fraction per gram. So fits you cannot combine the positive and negative number for defining a material. So if you want to specify the boron density in ppm, you have to convert the atomic fraction to mass fraction. So please change the atomic fraction to mass fractions and the boron 10 ppm boron 10. And the one important notice here, it's not directly related to the exercise, but this line. This line indicates thermal neutron scattering law data to consider the molecular structure of water for hydrogen evaluation. So in the neutron transport in human body, so most hydrogens are like a water, composed of the water. So it's better to use the hydrogen cross-section for water. And in that case, you have to add this line. This indicates water, light water. So, so this is why we add this line in this input file. But anyway, this is not related to the exercise. So let's do the exercise by changing the mass fractions and add boron 10. When you finish this exercise, please click the yes reaction button.
Hello, may I can
Yes.
ask?
Yeah, sure.
Thank you for allow us by mic. I just, okay, I did the exercise and I want to know about the line MT1 light water 20T below the material section.
Yeah. This is for like thermal neutron kernel, as I said. So
Mhm.
how to treat hydrogen cross section.
So if we skip this line, so will there be a big difference in results, or is there any option to skip?
Not that much big difference. So, but they're slightly change. This part, maybe you can try. So, this thermalization part is slightly changed, but it's hardly seen from this kind of graph.
Yeah, okay. So is this line is for all hydrogenous material or just
No,
only for water?
it's for water.
Only water.
So if you want to simulate like a polyethylene, then you have to define another one. And also, yeah.
So is this written in manual? Can we find this in manual for different material?
Yes.
Okay. Later I will check. Thank you.
So not finished yet. Maybe I would like to show the answer. Maybe this exercise is rather difficult if you don't use daily use fits. So the negative number indicates mass fraction. Positive number indicate atomic fraction. So negative number indicate mass fractions. And the two characteristics of mass fractions are the total atomic number of water molecule is 18. And 18 of 2s are hydrogen. And 18 of 16s are oxygen. So if you want to convert to the mass fraction, you have to write in this way. Of course, in precise sense, hydrogen includes not only hydrogen 1, but also hydrogen 2, so deuterium. So it's not as simple as this equation, but you can roughly approximate the mass fraction using this equation. And then add 10 ppm boron 10. And the 10 ppm boron 10 means 10 to the minus 5, because 1 ppm is 10 to the minus 6 gram per gram. So 10 ppm is 10 to the minus 5. So this is the answer for this exercise. So this material indicates that the water with 110 ppm boron 10. And once you change this and run fits, you will get this dose distribution. So in the previous case, almost no neutron dose, but if you only add only 10 ppm boron 10, neutron dose increase this much. So completely different. So now I think you can realize the importance of the boron existence of boron 10 in the dose calculation for low energy neutron beam. Okay, so any questions up to now?
Yeah, may I, please?
Yes.
Yes, maybe maybe not so significant. I mean, after adding the boron 10, so we assume that there is no change in density of water. It remains same, 1 gram per
Right.
centimeter.
In
Okay.
precise sense, maybe 1.0001,
Okay,
but yeah, we can ignore such
Ignore this.
small difference.
okay, yeah, thank you.
Any other questions? Okay, up to now. Okay, so let's move forward. So next exercise is set E mode equal to 2 in parameter section to enable neutron reactions. So basically, this is a little bit difficult point of fit simulation. So in the case of non-event generator mode, neutron dose is calculated by karma approximation. But if you use event generator mode, neutron dose is calculated by the charged particle, the energy loss of charged particle. So please add it mode equal to 2 in your input file in the parameter sections and run fits and see the difference between the E mode 1 case and the E mode equal to 2 case. Okay, so let's do this exercise. When you finish, please please put yes button. Okay, I think this exercise quite easy, but if you couldn't finish the previous lecture, it's rather difficult. So in such case, please go to the input folder and click the Bnct 3-3.inf. Then if you add E mode equal to 2 and run fits, Then I should change exercise 2. So I should do Bnct 2 and E mode equal to 2. Then
Eiko-san, so number 3 is input file for Boron 10 is added. Bnct 3.
3. I should do 3. Okay. So this one is correct. Okay. So now we can see P5 group under P5 group is actually this one. Sum of the alpha and the lithium 7. So it's equal to the neutron capture boron capture reaction dose. So now neutron dose disappear because, so people usually say neutron dose, but the term of neutron dose is sometimes like a controversy because neutron itself never deposit energy to a material. Always secondary particle, charged particle deposit energy. So if you turn on the event generator mode, secondary particles are explicitly generated. So in that case, neutron dose become 0, and the charged particle always deposit energy to a material. So lithium plus alpha dose here. And the proton dose is here. So this is a hydrogen recoil dose. So hydrogen in water is kicked out by neutron, so it deposits some amount of energy, but quite low. So next, let's try exercise 4. Define a human tissue material as material 2 and replace with this. So this is a mass fraction per gram of human tissue material given by ICRP report 44. So let's define material 2 with this ratio plus boron 10 ppm and change the material from water to tissue material. Okay, so let's do this exercise. So everyone's still working or finished? So if you finish, please press yes button.
Tatsuko-san,
Yes.
now it is okay. So I also do this exercise and I met some strange result. So
Oh, really?
because so I add the material number 2 and
Yes.
I forgot to add the LWTR.20T
Yes.
and the results of those EPS does not appear.
Really?
Yeah, but so if I comment out the MT1, so I obtain the result. So I feel it is strange.
Oh,
So
really?
yes.
Oh, that's anyone else has a similar problem?
Yeah, maybe I don't have this problem. The first time I haven't used this line MT light water T, but I got the result.
But I guess you use a little bit older version.
Yes. Yeah.
So
3.2.
maybe it's specific to 3.3 or 3.3, or I will try. That's if that is true. It should be a huge bug. We simply copy and paste some. Save.
And so please change the material number.
Material, yeah.
Yes.
This is a result you got,
No.
not the same one?
Yes.
Oh.
It depends on my environment.
Yeah.
How about the other guys? What kind of result did you get?
So I get without may I can share the screen?
Okay.
Thank you. You need to allow me. Okay. So
Looks much better.
so this is just a moment. So I forgot. One is no, this is the same thing. Just a moment. So this is without the line MTRT. This one is. Can you see now?
Yeah, I can
This
see.
is without the line MT2
Okay.
light water. This is with the line with light water.
Okay.
MTT.
So looks quite.
This is my my input file. You can maybe it of help.
Okay.
And so can you comment out the MT to other line number 34?
Yes.
Comment out and please run it.
Without that, this is the result. This one. Okay. I run again if you want.
Okay. Okay, I see. Well, it might be the reason why my result is different from you is depend on my PC.
But
I have the older version. I'm using older
okay,
version 3.22. I'm sorry. I need to mention it before. I am using 3.22.
Okay, I see. So can I?
Anyway, if I add is fine.
Okay.
It's
I'm sorry.
okay. I need to share my screen.
This is the result what I obtained. Yeah, so please see the spectrum EPS. Yes, this is the result what I obtained.
It's quite strange. It's a
Yes,
huge bug.
I'm not sure. I'm not sure, but anyway, so when I comment,
No, but actually I add. Now I add this.
Oh, really? Oh, I
Yes,
see.
and I got that result.
Oh, that's strange.
Really. Did you, Abe-san, did you use this input or you continue to change from here?
Yeah, I use the original one.
Original one.
Yes. Because I try to use the input Bnct-4. That result is strange. Okay.
Should be bug of the latest version.
So let's discuss later.
Yeah, let's discuss later.
Okay. Thank you.
Sorry for this problem. So anyway, what we expect to get is these two data. So this one is for this one is for the water, and this one is for human tissues. And the biggest difference is the proton dose, because in the human tissue, there is a nitrogen 14. So nitrogen 14 produce rather high energy neutron, high energy protons, roughly 0.6 MeV. So it deposits some amount of energy like this. So the conclusion from this simulation is the material composition is very important in the Bnct simulation, different from the X-ray simulation case. In the X-ray therapy simulation, human body is usually represented by water with different density, but that assumption cannot be used in Bnct dosimetry. In the Bnct dosimetry, you need to consider actual material composition. So that's a very important things. You have to be careful about the Bnct dosimetry. Okay, so let's go to the next part. So this part is rather different from the original part. So for those components of Bnct, so as you may know, Bnct dosimetry doses are distinguished by 4 dose components. One is boron dose. The second is gamma ray dose. Third is hydrogen dose. And the fourth is the nitrogen dose. And the reaction contribute to each dose are different. So for boron dose case, the boron capture reaction dose. X-ray dose is just a photon or electron, in precise sense, electron dose. And the hydrogen dose is a neutron elastic reaction by hydrogen, elastic or inelastic. And the proton is generated. And the nitrogen dose is, as I explained before, nitrogen-14 capture neutrons, and the protons and the carbon-14s are created with these reactions. And the reason why we distinguish these four dose components are their different RV between the doses. So RVs, I think most of you know. Oh, any questions?
Yes, if you allow, please.
Yeah.
So, so here I can see the boron dose is little bit higher for the skin compared to brain, normal dose in brain.
You mean previous dissimulation?
No. The current slide.
Yeah.
We can see the left figure, the second column,
Yeah.
normal dose brain.
Yeah.
And normal dose skin.
Yeah.
The boron dose in the skin is bit higher than normal dose in brain.
Yeah.
So I cannot understand why. Would you please?
Okay. So this is simply because I will explain later.
Okay, thank you.
Yeah. So this is maybe so. First, I need to explain about the RV. So I think most of you know about RV, relative biological effectiveness. So even the same absolute dose, the biological effectives are quite different. So for example, alpha and lithium both are very high LET particle. So generally, RV is quite high. And protons created by these reactions are also rather high LET. So they are also high relative biological effectiveness. And the electron generated by photon has low LET. So the RV is quite low. Actually, this gamma ray dose is generally used as a reference dose. So RV is defined as the ratio of the gamma ray dose to those other dose. And so that's why we need to distinguish these doses, because at the end, you have to multiply RV to get the actual therapeutic or normal tissue effect to patient. So, and then boron dose depends on the boron concentration. And the boron concentration is usually different from tissue by tissue and also tumor. So in general, a lot of borons are taken into the tumor. So that's why you see huge boron dose here. And the boron is generally not taken into brain. So the boron dose in normal brain is quite low. And the skin is rather high boron concentration. So boron dose is slightly higher than the brain. So that's why this becomes different. And the principle of Bnct is basically they use this difference. So even every part gets the same absorbed dose, except for the boron component, only tumor got high dose like this. So that's why we can use BNCT as a therapy. Okay. Okay, so next, I would like to talk about the CVE and RV factor. So as I said before, RVE is different by radiation. And in addition, in the Bnct case, it's a special quantity called compound biological effectiveness, CBE, was introduced. Because, as I said before, the boron concentrations are different by tissue. So this CBE factor includes the boron density and boron RBE too. So for example, PPA for tumor, boron density is high, and also boron concentration is high. So the CBE factor is quite high, 3.8. But for example, PPA in brain, the RB is high, but the boron concentration is generally low. So in that case, CBE can be lower, even sometimes below 1.0. This this number comes from somewhat empirical factor based on the result of clinical result or animal experiment. But we usually use these number to weight on the boron dose. Okay, so, and also the gamma ray dose and the hydrogen dose RV factors 1 and 2.5, and nitrogen dose is 2.5. Okay, so let's do the exercise 5. Run fits with Bnct each dose imp and calculate 4 dose component. So with this input file, you can separately estimate the boron dose, hydrogen dose, nitrogen dose, and the photon dose. But the CBE or RV factor is not multiplied yet. So simply, this is a absorbed dose. So, okay, let's run this input file and check the result.